All right, 1 second, let me get my screen up here so I can start presenting. All right, I kind of missed this. I don't know how to work PowerPoint, I guess is the main thing here. So we're gonna not look at it in presentation mode so I can still read some of my notes, but here is a review video for Chem 105 with Dr. Mortensen having to do with energy, heat, and work. All right, here we go. To start, let's talk about the first law of thermodynamics. The law is that the total change in energy in the universe is equal to zero. Basically what that means is that energy cannot be created or destroyed. It's kind of like the law of conservation of mass, but with energy. So it's also known as the law of conservation of energy. This delta sign, this Greek letter means change. And in this case, so the change of the energy of the universe is always going to be zero. It's constant. There are three types of energy. We've heard of at least two of these many times since we've probably been in like 7th grade. Potential energy, kinetic energy. Potential energy is the energy stored in an object due to its position or chemical composition. As you can see here in this little diagram, there's this roller coaster, and at the bottom of the hill, due to the position of the car, it has zero potential energy, and because it's an object at rest, it also has zero kinetic energy. Kinetic energy is the energy of motion, and the formula is this: 1/2 the mass times the volume squared. And as potential energy increases, kinetic energy doesn't always have to go down. In this case, kinetic energy would also be increasing. But by the end of the roller coaster, when this thing finally comes to a stop, the potential energy and kinetic energy will have evened out, so that way the first law of thermodynamics holds true, so that the change in energy in the universe is still equal to zero. Anyway, so as you get to the top of the hill, potential energy is really high, and gravity pushes you over the hill, down the roller coaster, increasing your kinetic energy, as you can see here. And your potential energy starts to decrease because it's no longer as high in the air, less potential for it to travel and move. And when you get to the bottom of the hill, this thing's cooking. The kinetic energy is really high, potential energy is really low because it's really close to the ground, less gravity to push it down. Last type of energy is radiant energy, and that's just light. We learned a lot about that in like the first unit. But all right, that's probably enough talk about energy, types of energy. Just kidding. Potential energy, like I just said, it's due to the position or composition of a molecule or an object. Chemical potential energy is an energy that exists because of the positioning of the atoms. So like there's different ways you can position molecules to give it higher potential energy. It also just depends on what it's made out of. Like that's the composition part. And so it doesn't always have to be with like things like balls bouncing or roller coasters. It can also just mean like the positioning of the atoms and like its different isomers and things like that. Kinetic energy, like I said, energy of motion, formula 1/2 the mass times the velocity squared. At the molecular level, there are three types of molecular motion represented here in vibrational, rotational, and translational motion. Vibrational, as you can see, it just shakes. Rotational, it rotates. Translational, it moves. In solids, you're only really going to see vibrational motion, but solids still have kinetic energy, and that's important to understand. So each one of those individual molecules right here is still vibrating back and forth constantly. The only way it will not is like if you're at absolute zero, and that's impossible. So even solids have kinetic energy, even though they might not seem like it. Obviously liquids, they flow, they move, they have kinetic energy, they rotate and translate and whatever else, and gases obviously even more so than liquids. And here I want to point something out, this little relationship between, if you can read that, it says kinetic energy and particle motion. So the more particles move, like I just said, the more kinetic energy it's going to have. Kinetic energy is also, the average kinetic energy is directly proportional to temperature. And that makes a lot of sense when you look at this diagram, because obviously liquids are hotter than solids, gases are hotter than liquids. So as temperature goes up, you go from solid to liquid, liquid to gas, kinetic energy also goes up because the particles are moving faster. And so that also has to do with like the force of attraction between molecules, like the intermolecular forces go down with lower temperature. I mean, they go up with lower temperature, and they also go up with lower kinetic energy because they're have more time to be next to each other and have that attraction. Okay, internal energy. This is the total energy of a molecular system, combining kinetic energy and potential energy, or in other words, the energy of motion combined with the stored energy due to position and composition. You measure this energy in a couple of different ways. Very common way is joules, and that it's just 1 kilogram meter squared per second squared. And then we have liter atmospheres. We'll talk more about that when we talk about work, but that basically or that converts to 101.3 joules. So later on, when you get to enthalpy, that will be important information for you to know. In calories, that is equivalent to 4.182 joules. 1 calorie is the equivalent of the amount of energy that it takes to raise the temperature of 1 gram of water by 1 degree Celsius. So these calories with the lowercase c, as you can see right here, are not the same as like food calories. 1,000 of these calories is the same as 1 food calorie. And like it's dumb, but the only way to distinguish one of these calories to a food calorie, it's not like you put like kilocalories or anything. You can put that like KC right here. But you just put an uppercase C instead of at the beginning of the word calorie. So if you see uppercase C, it's 1,000 calories. So yeah. Okay, system and surroundings. Let's talk about what the difference is. So let's think about an ice cube. An ice cube sitting on the counter, melting. Okay, that's our example. An ice cube sitting on the counter melting. The ice cube is the system, and everything around it obviously is the surroundings. The system, if we're measuring, like, let's say the temperature of the ice cube as it melts, or the change in volume, or anything like that, we're studying it, so it is the system. Everything that we're not studying then becomes the surroundings. The 3 types of systems are here in this little diagram. We'll start with open system. Open systems, let's imagine you have a pot of water boiling on the stove, and in order to make soup, you got to add all of your ingredients, right? That is an example, and turn up the heat so you can cook all the ingredients. That's an example of an open system where heat and matter can be exchanged. You can put things in, take things out. You can increase the heat on the inside. Heat can decrease if you leave it there and cool off. That is an open system. A closed system would be if you just put a lid on top of the pot. You can't take anything in or out, put anything in or out. Like you can't add ingredients if the lid is on the pot, but you can still lose energy or heat and gain energy and heat. An isolated system now is when you can't do either. You can't exchange energy, and you also can't exchange matter. An example of that, I guess, in real world applications would be like if you took your soup and you put it in a thermos to take and eat at lunch later that day or something. In an ideal world, like that thermos is completely tight, so you can't get anything in or out of it. And because it's tight and completely insulated, the heat isn't going to change either. So that's what an isolated system would be. Technically, the universe is an isolated system because there's no, you can't create or destroy energy nor mass. So the universe is also an isolated system. Changes in energy. Okay, so this delta again is changed. So change in energy is measured by taking the final amount of energy minus the initial amount of energy. It's very simple. Every time you see a delta in a letter, it's pretty much going to be like the same equation, but replaced by whatever that variable is. It's going to be the final minus initial. So delta, think finite minus initial. And energy is also a state function. And so to explain what a state function is, I have this hiker right here. Looks like they're lost. So let's say this hiker right here goes on a hike with her map. Okay, she's not lost. She has a map. I'll get lost. She has her map, so she can follow the trail exactly how it's supposed to be. She gets from point A to point B in one way, and great. But me, I am dumb. I didn't take a map or a compass. I don't have all trails. I didn't download the map or whatever. And so I go and I get lost. And let's say the trail is a straight line from point A to point B. Because I don't have my map, instead of going straight through, I take this really roundabout way with a bunch of different curves and bends, and I get lost a couple times. Have to like climb down a cliff, whatever it may be, but I still get to the destination eventually. So that's essentially what a state function is. State functions don't matter about the path you take, just that you get there. And so it's applicable with energy, the change in energy, because we're only measuring the final energy minus the initial energy. So it's like, it only matters like point B minus point A, if you want to think about it like that. Nobody asked like how far in between I went. I probably traveled a lot further than this girl did in the picture because I got lost, but nobody really cares because we both started at point A, got to point B. And that's what a state function is basically telling us. Okay, how internal energy changes. Delta E is equal to Q plus W. Q is heat. It is representative of heat. The flow of kinetic energy from a warm object to a cooler one. So it's not temperature quite. It's the flow of kinetic energy from a warm object to a cooler one. Work W, like I mentioned earlier, it's, never mind. In physics, it's force over a distance, but for our purposes, we're going to look at it as negative pressure times the change in volume. Negative P delta V. So basically heat can be interpreted as, energy, the change in energy, it can be interpreted as heat plus work, or the capacity to do work and transfer heat. Now we got to talk about endothermic and exothermic processes. Here is our equation again. Delta E equals Q plus W, heat plus work. If Q is greater than 0, if Q is positive, that means that the process is endothermic because it's gaining heat, okay? If Q is negative, that means that it is exothermic in relation to the system. So here, let's look at our ice cube again. If it's melting, it's gaining heat. Q is positive. Heat's going into it. Let's think about like a log burning. It's releasing heat. It's exothermic. Endo, think of coming in. Exo, think of going out in relation to your heat, and also work. Work is pretty much the same, but so if work is done on the system, let's say I have a balloon in my hands, it's blown up. If work is done on the system, that means I'm compressing the balloon. Let's say the balloon is the system and the process is endothermic. That means work is being done to the balloon, work is going into the balloon, the energy is increasing. If work is negative, that means work is done by the system on the surroundings. The balloon expands in my hands and the process is exothermic. work is done, it's going out. So when work is done by the system, it expands. When work is done by the surrounding, it compresses. And so compressed and going in, expands going out. Endothermic, exothermic. All right, phase changes, just a quick overview. So you'll probably, it's easy just to think like if it goes from cold to hot, basically. Think of if it goes from cold to hot. So cold to hot right here, melting, endothermic, gaining heat, cold to hot. Liquid to solid, it's getting colder. So hot to cold, and that's exothermic. It's releasing heat, getting colder. Liquid, again, it's getting hotter, gaining heat, vaporizing. Gas is getting colder, releasing heat, condensing into liquid. Solid is sublimating into gas, gaining heat. Gas is going through deposition, going to a solid, and that's exothermic because it is giving off heat and going into a solid. All right, to explain a little bit more about work. Like I said earlier, work is measured by negative P delta V. This little EXT right there means exterior, the pressure of the exterior. So if delta V, if the change in volume is negative, like I said, that means it was a compression and work will be positive with our balloon. So change in volume, I compress the balloon, volume decreases, it's negative, and work will be positive because there's now more energy inside the system, more work that can be done. If delta V is positive, that means it was an expansion and work was will be negative. So work was done on the surroundings by the system, releasing energy in the system, it's negative. And so that's the whole reason why this negative right here exists with the equation, because if the change in volume is positive, work has to be negative still, right? Because the system did work on the surroundings, but unless we had this negative here, work would be negative still. I mean, it'd be positive when it's supposed to be negative, basically. So it's just to make sure you have the sign right. Don't think about it too much. Okay, I think that, okay, positive work means that the surroundings are doing work on the system, and negative work means that the system is doing work on the surroundings, like I just said. Okay, quick practice problem here. Calculate the work associated with the expansion of a gas in a cylinder from 25 liters to 50 liters against a constant pressure of 5 atmospheres. So like I said, the equation would be W equals negative P times delta V. Delta V is the change in volume. So you take the final 50 minus the initial 25. So the pressure of the exterior, negative 5 atmospheres. The change in pressure, 50 minus 25 will be 25. So 25 times negative 5 give you negative 125 liter atmospheres. And that's where that unit comes in that we talked about earlier. Okay, enthalpy. We're almost there, ladies and gentlemen. Enthalpy is a measure of internal energy combined with the energy expended to push aside the surroundings to make space for the system. It's this equation right here. So it's energy plus pressure times volume. It's not possible to measure enthalpy H unless it's at constant pressure, and that's represented by this series of equations here. So we can only measure delta H if it's at a constant pressure because of this. So we have the change in energy here plus the change in pressure times volume. This is assuming that the fact that this pressure is inside the parentheses is assuming that it's going to change because of that delta sign. But if we make it constant, it then goes outside of the delta, which is going to be important right here in a second. And E, delta E, like I said, is Q plus W. W is represented by negative P delta V. Up here we have P delta V. So negative P delta V plus P delta V, they just cancel out. And so the way we actually measure a change in enthalpy is just delta H equals Q. delta H equals enthalpy equals your heat. And if enthalpy is greater than 0, the process is endothermic. If it is less than 0, it is exothermic. Okay, last slide here. Enthalpy of phase changes. Enthalpy of vaporization is the energy needed to convert a given amount of liquid at its boiling point into the vapor state. Enthalpy of fusion is the energy needed to convert a given amount of a solid at its melting point into the liquid state. We're not really gonna have to do too much with that right now, but in a couple of sections that would be really important. So for now, just keep in mind that there are different kinds of enthalpies and different delta H values that we're going to be dealing with. And that's pretty much all you'll need to know. But that is my review. Hopefully it's helpful for you guys. Thanks.